with respect to s. Understand? That's the whole tree filled out. So what did you think this one was going to be? Did you have an idea?
Partial z, or no, yeah, partial z over partial x.
Okay.
Plus times partial x over partial y plus partial z over y and times partial y over r.
Yes, you got it. So this is it. This is what we're going to do. We need to go, since we're going from z's to r's, right? I need to come down all branches to get me down to these r's. So I need to come down partial z with respect to x times, because I'm coming down a branch, partial x with respect to r. That'll get me down this way, right? Plus, then I come down to get to this one, down here into there. So it'll look like this. Coming down this way, partial z with respect to x times partial x with respect to r, plus partial z with respect to y times partial y with respect to r. Notice that we don't even look down the partial x with respect to s and partial y with respect to s. The reason why we don't do that is because if you're looking at the partial of z with respect to r, what are you holding constant? You're holding s constant, aren't you? If s is a constant, right? If s is a constant, right? If s is a constant, then this branch right here, right, is going to be zeroed out when you take a derivative. So it's not even going to matter. So there it is. Now, let's do the other one. Let's see if there are any other colors in here. I don't see green. Let's do partial z with respect to s. So what would the difference be in my picture? There's a green one over there? Oh, there we go. Good. There's one where? Oh, I didn't see that one. Okay, so the only difference here is that we got to get down to the s's, right? So the path we take still starts here. We're going to come down here, and this time we're going to go down this side. Come down here and this side, right? So the two pieces that'll be the same are the partial z with respect to x will still be there. The partial z with respect to y will still be there. These two pieces are going to change with respect to s and s, yes? So partial, I'll do it in green. This is partial z with respect to x, but now partial x with respect to s, plus partial z with respect to y times partial y with respect to s. Those are the two derivatives that are possible, and there's the formulas for each one. Is this clicking? Yeah? Okay. Let's try and compute one of these. Let's do an example. What example is this? Is this example 3 or 4? Example 4? All right. Ah, come on. Okay, z is equal to x sine xy. X is equal to t squared plus 4, oh. Okay, x is equal to r squared plus 4s. And y is equal to the natural log of r times s. rs. That's multiplication in there. So if I'm starting this problem out First time I'm looking at it, you know, z depends on x and y. Okay, x depends on r and s. Y depends on r and s. Right? So I'm going to draw my quick tree. See, at some point this becomes quick. X, Y, R, S, R, S. And so the possible derivatives, there's two of them, right? I'm only going to do one of them, all right, because I don't have time for both. We can do partial z. You want to do it with respect to R or S? R. Which, if I follow my tree down, I'm just going to show the pictures for this particular one. Partial z with respect to x, partial x with respect to r. Then I'll do partial z with respect to y. That's a terrible marker. And then partial y with respect to r. So this is partial z with respect to x times partial x with respect to r plus partial z with respect to y times partial y with respect to r. You ready? This equals. What's the partial z with respect to x? We've done this already, right? This was sine x, y, plus xy sine x, oh, cosine xy. Okay, that's just this piece. What's the partial of x with respect to r? Well, that's a nice one, right? S is a constant, so just 2r. I like that. Plus, what's next? Partial z with respect to y. We've done that already, right? X squared cosine xy. And then partial, yes? Partial y with respect to r. What's the derivative of natural log of rs? 1 over r times s times the derivative of the inside with respect to r, so hold s constant. What's the derivative of rs if s is constant? S. And the s's cancel here. So this is just 1 over r at the end. And then what would you do? Replace all your x's with r squared plus 4s, all your y's with natural log rs. You rewrite the whole ugly thing, and that's your derivative. It will have two variables in it when you're done. What should those variables be? R and s. That's it. Got it? Okay. You sure you got it? You think you got it? Yeah, I mean, there's no hidden magic in this at all. All right.
That's all to do, like find the partial derivative for z with respect to r and then z with respect to.
Yeah, there would have been another one. I just because of time I didn't do it.
So then what do we do with those? Do we find them?
That's it. All we're trying to do is say, is there a way to find the derivative of a function that is actually a function of more than one variable and depends on things that might possibly be a function of more than one variable? Does it still make sense to talk about instantaneous rates of change? I mean, we know when you go back to Cal 1, right? I hate to go back to this and keep harping on it, but when we have a function, right, and you're trying to find the derivative, it represents the slope of the tangent line. It was the instantaneous rate of change. It was dy dx, yes? The way we got that is we imagined a separate point over here, and we drew a right triangle, and we basically said that this base side was the change in x, delta, and this was the change in y, right? And so when you do like slope of this line, it's going to be the change in y over the change in x. And then if you let this triangle get infinitely small, right, infinitesimally small, this delta x became dx, and this became dy, and that gave you the derivative, dy dx. And that's what happens when you move that point on top of the other one. So the idea was that if x changes just a little bit, right? If I just move a little bit to the right, then my function is going to go up or down, right? And that change, that slope, that change was the derivative. So if x changes, y changes. And this represents the amount at which the amount that y will change. This is saying if z depends on x and y, and x depends on r and s, and y depends on r and s, then if I just move r just a little bit, right? If I just allow r to just change a little, how much will z change by? That much. You see? That's the formula to compute that change. If I change s by a little bit, how much will z change by? And so it's still an instantaneous rate of change. Does that make sense, Kieran? Okay.
I just wanted to know like what you're trying to get.
Yeah, we're not trying to now like solve and get a number or anything. It's more of, can you come up with a formula that will represent the derivative? We actually aren't even going to really mess with it too much. But this is a generalized chain rule. This is what it is. It's a generalized chain rule, which is why this section is called chain rule. You could almost in Cal 1 have started with this idea, but of just drawing a picture. It just would have been too much. So you ready to try and generalize this? Yes.
When we're at the end, when we have to rewrite it,
Uh-huh.
in terms of like R and S,
Uh-huh.
we have a function as S, R, and S, do we have to adjust that, or are we leaving it both?
If it has a function that what?
Like X was R squared plus
Mhm.
4S,
Uh-huh.
and we solved for R on one of
Mm-hmm.
them. Are we still leaving that S in there?
Yes, you would have R's and S's in your answer. And that's because you're holding S constant, right? But in order to actually find the derivative, you would have to know what that constant was being held at. Okay, can we come up with a general idea, a general formula for this, all right? So let me try it by drawing a picture. All right, what if we have Z up top, right? And Z depends on a couple of things, right? Like X and Y, or maybe it depends on more than just X and Y. How about if Z depends on X1 and X2 and X3 and ... all the way out here to Xn. So let's say Z depends on n different things. We've only dealt with one case. Well, we've dealt with two cases where Z depends on one thing or Z depends on two things, right? X and Y. But what if Z depends on n things? And what if each of these depend on, let's say, T1? And this one depends on, let's say, T2. And let's say to Tm. Now, I'm not going to use n and n. These are different numbers. Because this one might depend on three things, where this one might depend on five things. Understand? So I'm using subscripts instead of x and y because if I use subscripts, I never run out of letters, right? This x2 also depends on T1 through Tm. This x3 depends on T1 through Tm. Make sense? This xn depends on T1 through Tm. What derivatives would be possible here? What derivatives would be possible? dz. So z. What does z depend on here? What does z depend on? Depends on ultimately T1, 2, 3, all the way to Tm, right? Yes? So what's possible here is partials of z with respect to t's, right? I'm going to say ti's for I equals 1, 2, all the way out to what? M. Do you agree with that notation? This is what's possible. there are how many partial derivatives possible for this situation? M of them, right? I could have partial z with respect to t1, partial z with respect to t2, t3, t4, all the way out to tm. Yes? Can you give me a formula for the ith one? For the ith partial derivative. Let's see if we can. So let's just pick one. Let's just pick an I in here. Do you agree that a ti would be somewhere in here? I mean, if I is 1, of course, it's the first one. If I is m, it's the last one. But we're just trying to come up with a general formula. So there's a ti in here. There's a ti in here. There's a ti in here. So what would you have to do? You'd have to get down to each one of those, wouldn't you? Yeah? So let's go down. Let's get to this one. What would it be? What's this branch right here? Partial z with respect to x1. And then down this branch right here, partial x1 with respect to ti, right? Plus, then you have to come down this way, which would be partial z with respect to x2 times partial of x2 with respect to ti. And then you do it the rest of the way. Make sense? How many of these you would go all the way out until you got to partial of x? Okay, so let's see if I can write this out. I don't know if you'll be able to keep up with this. Let's see. I have to erase the picture. Oh, maybe I can put it down here. The partial of z with respect to ti would be equal to, like you just said, partial of z with respect to x1 times partial x1 with respect to ti plus partial x2 with respect to, partial what? I screwed that up. Where am I? Coming down this branch now, right? Partial z with respect to x2 times partial x2 with respect to ti. Y'all still there? Do another one. Plus partial z with respect to what? x3. So I'm coming down this one now. x3 times partial x3 with respect to ti, right? Plus, I keep doing this, until I get to the very last one, which would be the partial of x sub n, z, over partial x sub n times partial x sub n over partial t sub I. That would be it. Go ahead. You don't have to explain. Go ahead. This good? That's a general formula. Now, just out of curiosity, what would happen if each of these t's depended on like R1, R2, all the way to like R, let's see, I've used N and M. How about if I go R sub K? You would have another piece to each of these, right? But even more than that, you would have an additional branch for each one. So like, you would have to go down here, and then once you got here, you'd have to go down each branch. Oh, man, disaster. But you could see how this could generalize, right? And there's no restriction now how many variables your z depends on. It can depend on 1,000 variables, and each one of those depend on 50, and each one of those on 10, and each one of those on 20. And what happens is you can still find a way to determine instantaneous rates of change. You just got to be able to tree it out and figure out what branches to go down. All right? Exciting stuff.